Hello students, welcome to the online lecture 4 of the course Introduction to Microwave and Optical Metamaterials. So, today's lecture will be a continuation of the classifications of metamaterials that we discussed in the previous lecture. So, here is a brief outline of the lecture. So, we will continue with the classification of metamaterials based on functionalities. We will go into details of electromagnetic metamaterials and focus on intelligent metamaterials and quantum metamaterials. We will also have a better understanding of acoustic metamaterials, how those can be used for acoustic cloaking and acoustic cloaking carpets. We will also see how thermal metamaterials work and what are the mechanical metamaterials. All these things are important for you to get a better picture of the capabilities of metamaterials and to make you understand that this particular domain is not only related or limited to microwave and optical, it is rather metamaterial concept is applied in other engineering disciplines as well, as you can see in the acoustic area, in the thermal, in the mechanical and so on. Okay. So, let us go into the details of electromagnetic metamaterials and look into how intelligent metamaterials work. So, they are basically used for smart sensing. So, we have seen in the last decades or so that several information metamaterials have been proposed which still require human beings to give instructions and produce pre-designs to perform some specific functions. So, smart metamaterials which can sense the surrounding environment and the information in real time and can actively make adjustment themselves have become the main target of modern day research. So, you can understand that these materials are responsive dynamically to the surrounding information in real time, right. So, smart metamaterials can sense changes in the external environment through sensing elements and realize autonomous judgment and active adaptation via a feedback loop. So, here you can see from the figure, it shows smart metamaterial with the function of self adaptation without manual instruction. So, what is shown here is the satellite and there is an aircraft, okay, which has got some smart metasurface integrated with its gyroscope to sense the flying direction, right. So, what is happening here is shown in figure B, that you have basically got a feedback loop of this intelligent metamaterial which is composed of a digital coding metamaterial, then you have got an FPGA. So, an FPGA is basically a digital IC that can be programmed to perform specific operations after manufacturing. Okay. So, it allows for customization and reprogrammability, okay, or reconfigurability. So, FPGA stands for field programmable gate array. Okay. So, then you have a sensor and you have a microcontroller based MCU, microcontroller based unit which is loaded with a feedback algorithm. So, this is how the loop works. You have got a sensor which is a gyroscopic sensor, okay, and then it goes to the feedback algorithm, then you basically readjust your metasurface and that is how it works. Okay. So, this is a situation what I just described. It is a situation where an aircraft equipped with this kind of smart metamaterials can communicate with a satellite that is shown here. So, here in this particular example, the integrated sensor is a gyroscope sensor that basically detects the changes in the flight direction or flight status of the aircraft, which is represented by the rotation angle of the metamaterial, and instantaneously or instantly it can transmit that information to the microcontroller. And then what happens, the microcontroller basically instructs the FPGA to calculate the digital coding pattern that is required on your metasurface, okay, according to a preloaded feedback algorithm, and that will ensure that the radiation beam keeps on focusing to the real target object in real time. So, here you can see that when the aircraft is this way, the beam is focused towards the satellite. When it comes here, the beam got adjusted and again realigns with the satellite, and so here, so also happens here. So this is how a reconfigurable intelligent metamaterial works. So what is the fun? So we are basically working with smart metamaterials. Okay, so the good thing here is that you can make things work and change in real time, and that is the fun part in this particular intelligent metamaterials, right. So here you see the schematic of a smart metasurface, which is basically composed of the sensing units, which are S units, and also there are some executing units or E units. Okay. So what happens under the incident of different polarization? So the red one shows X polarization, the blue one shows Y polarization. Okay. The sensing units are able to recognize the incident power levels and transmit the data to the microcontroller unit for digitizing. Okay. So that is what is the sensing unit doing, and after collecting the data, the FPGA is able to determine the coding sequence independently on the specific polarization and drive the executing units to realize the desired scattering pattern, and that is how it works. So you have got the sensing unit that is giving to the microcontroller, they are getting the sensing data which is transferred to the FPGA for the calculation, and then it is basically giving you the coding pattern that is required to program the metasurface for behaving to a particular polarization. So here the FPGA modulation can also be achieved by using PIN diodes. Okay. So you are basically integrating the PIN, those are also called pin diodes. So I stands for intrinsic. So here you have a wide undoped intrinsic region between your P type and the N type region. So that is how you make this PIN diodes. So when you integrate pin diodes on two orthogonal directions, both E units and the S units can modulate the phases independently. So that is the good thing here. So you can modulate the phase response independently, which guarantees excellent capabilities to control the scattering fields. Okay. So according to the power levels from the sensing data, your metasurface can generate various scattering fields based on the pre-designed algorithms. Another type of electromagnetic metamaterial which is also booming is quantum metamaterials. So here we have understood that electromagnetic metamaterials have shown very high degrees of freedom to control classical electromagnetic waves. Such a flexible and powerful manipulation capability can be further used to significantly promote the development of fundamental science and engineering technology, also in the non-classical electromagnetism regime, that is where we are stepping into the field of quantum information science. So in recent years, quantum information science has also developed very rapidly, and its superiorities has been established in information communication, measurement, sensing, computing and other different aspects which are expected to revolutionize the current science and technology. So that is why a lot of researchers are currently working on these quantum technologies. So this innovative quantum technologies can get further advanced by using electromagnetic metamaterials or EM metamaterials, and that has led to this new field of quantum metamaterials. So till now, quantum metamaterials have become a revolutionary extension of the classical electromagnetic metamaterial concept, and it has provided an important physical platform for the generation, manipulation and detection of quantum information. Just like the classical electromagnetic metamaterial allows you like manipulation of electromagnetic waves or information, in the quantum domain you are also getting the similar kind of effects. So quantum metamaterials are a very new concept bridging the traditional metamaterials and the quantum technologies, and they are also a new type of artificial atom, or you can say meta atoms. So here this particular picture shows the concept of quantum coherence. Okay. So, it basically allows preserving coherence in quantum systems, okay, because it is very crucial for quantum computing, communication and sensing. Okay. So, here you can see that the information is coherent, but because of some disturbance the information decoheres here. Okay. So, this is basically a repeating pattern. So, coherence, when we talk about coherence, coherence is basically a measure of how well the objects maintain their relationships with each other and how well the system's evolution can be predicted. The longer a system, here it is basically represented mathematically as waves, okay, remains coherent the longer it has to process the information. Okay. So, coherence is fragile and it is hard to protect, because you can see here little disturbance can break the coherence, right. So, when a quantum object encounters environmental disturbances, the information stored in the coherent system is basically lost in the process called decoherence, and scientists are basically working towards preserving coherence in quantum systems such as computers, networks and sensors. So, what are the examples of this disturbance factor? That it can come from impurities in material, it can come from particles, external electromagnetic waves, mechanical vibrations and also temperature fluctuation. So, you see the coherence is basically a very sensitive thing. Okay. So, with that understanding, we can see that quantum metamaterials and their coded units, which are basically qubits, okay, have typical physical properties of quantum states such as quantum coherence, and the quantum states of these units can be externally controlled. Meanwhile, the system of these artificial atoms can maintain quantum coherence on the time scale of the electromagnetic pulse propagation across it. So, in general, you can say that the quantum metamaterials basically include superconductor quantum metamaterials, nonlinear quantum metamaterials, space-time quantum metamaterials and so on. So, many new concepts coming in. So, we will not go into so much details of all these concepts in this course, but yes, if you want to study further or research further in this particular domain, which is very new and upcoming, you are very welcome. Okay. Due to their low loss, compact structure and strong nonlinear properties, semiconductors have become one of the most widely used platforms for quantum metamaterials. Currently, semiconductor quantum metamaterials have broad application prospects in the field of single microwave photon detection, quantum birefringence and phase transition of quantum superradiance. So, let us take some examples of this quantum metamaterials in the field of, say, we will begin with quantum imaging. So, quantum imaging systems basically utilizes spatially entangled photon pairs, which demonstrate the potential to achieve high resolution and high sensitivity, surpassing those you can get from the classical optical methods. Okay. So, quantum entanglement is basically considered as one of the most powerful resources of quantum information. In this respect, pairs of photons are the simplest systems showing genuine quantum entanglement in all their degrees of freedoms, such as spatial, spectral and polarization. So, a team led by Professor Andrei A. Sukhurkov, he presented research findings on quantum imaging of two-dimensional objects using spatially entangled photon pairs, which are generated from non-local nonlinear metasurface composed of a one-dimensional grading structure that is shown here, right. So, what happens in this particular case, I will explain. So, this study basically presents the first demonstration of utilizing nonlinear metasurface based on quantum photonic structures for quantum imaging. There are a couple of new terms here. which we need to understand. So, we will go one by one. So, here you need to understand that the team employed a lithium niobate metasurface with sub-wavelength scale silica matte grating on it to achieve enhanced SPDC, okay, which is nothing but spontaneous parametric down conversion for the generation of spatially entangled photon pairs. Okay. So, what is SPDC? It is basically not a popular technique to produce spatially entangled photon pairs. So, in its conventional form, a coherent Gaussian beam, okay, of light considered to be the pump beam, as you can see here, okay, illuminates a nonlinear crystal which has got, say, chi-square nonlinearity, and that produces pairs of photons in accordance with energy and momentum conversion, right. If you see this particular figure, okay, you can see the optical setup shown here for quantum imaging. So, in this particular figure, you see the optical setup for quantum imaging with spatially entangled photon pairs from a nonlinear metasurface, which is shown here. So, the 2D imaging of the object was obtained via quantum ghost imaging and all optical scanning in the z and y direction, okay, respectively. So, what is quantum ghost imaging? It is basically a technique that allows you to reconstruct an image of an object using light that has not directly interacted with it. So, this is achieved by exploiting the correlations between the entangled photon pairs, where one photon interacts with the object while the other is detected to reveal the information about the object's spatial distribution. Okay. So, in figure B, you can see the experimental data of 2D quantum imaging combining ghost imaging and the optical scanning. So, the top and the bottom panel basically shows the camera, which is the classical image of the object, and this one is basically the quantum, reconstructed image from the coincidence measurement. Okay. So, the unique properties of the metasurface basically enabled a hybrid quantum imaging approach. So, what do we learn from here? That the quantum ghost imaging along the z direction, which is basically parallel to the stripes of the grating, okay, in this particular figure, was realized using the broad anti-correlated emission patterns of entangled photon pairs. Then all optical scanning along the y direction, which is basically perpendicular to the grating strips, okay, was achieved by tuning the photon emission angles through adjustments to the pump laser wavelength based on the dispersion dependent behavior of this known local metasurface. And based on these characteristics, the experimental implementation demonstrated the feasibility of high resolution 2D imaging using 1D detector array. So, you can see these are SPD, single photon detector, okay, and here you have SPD array. Okay. So, you can see the signal and the idler coming like this is the pump. Okay. So, the single photons or the signal photons, these ones, okay, generated from the metasurface basically pass through a 2D object that you see here, okay, and that is where this particular object will be, okay, any object that you want to image, okay, that will be kept here, and it will be detected by a bucket single photon detector SPD, while the idler photons, which basically come this way, okay, are detected by an SPD array in the z direction, right. So, you have an array in the z direction. So, by measuring the coincidence as a function of the photon wavelengths, this 2D imaging data can be reconstructed. So, the figure B basically presents the results of this 2D quantum imaging combining the ghost imaging for the z pixels and optical scanning images along the y. Okay. So, these are the z pixels, okay, and these are the y. So, this is where you are scanning optically, but the z one are basically the ghost pixels, and both are combined to give you the kind of image of the object. So, with that we move on to the another application of metamaterials in a different domain, acoustic domain. Okay. So, here the acoustic metamaterials are basically inspired again by electromagnetic cloaks, because we are taking the example of acoustic cloaking metamaterials, ACMs. So, they are firstly designed as a shell with a gradient bulk modulus, as you can see, and mass density. So, you have gradient bulk modulus and mass density that allows the acoustic waves to bend around the object, okay, that you want to hide. So, that is very similar to the concept that we have seen in the previous lecture for light. Okay. So, this particular clocking solution was capable of controlling the scattering of the compressed acoustic waves, so that the wave could bypass the shell without scattering. So, you see the way the waves were coming, they are exiting in the same manner as if there is nothing over here. Okay. So, the cloak was fabricated by machining an aluminum plate into 16-step piecewise homogeneous cylinders that gives you gradient bulk modulus and mass density, as you can understand. So, this is a zoomed diagram, and it shows the measured pressure field mapping of this particular cloak at 60 kilohertz. So, you can see that this object is not actually disturbing the field at all. Okay. So, the same concept can be further extended to make carpet clocking. So, this is a new way to realize acoustic invisibility. That was also something similar to the cloaking, carpet clocking that we have seen in the previous lecture on optical domain, where that lady was holding that carpet which was hiding her body in the path and was revealing the background. Okay. So, the same kind of concept can be used here. So, in general the 2D acoustic carpet clocking is basically shaped like a carpet, on the surface of which there are a series of well designed microstructures, as you can see here, that could basically compensate for the phase distortion caused by the geometry of the carpet clocking, right. So, how it works, the whole idea is, say if you want to hide something below the carpet, so the elements on top of the carpet should scatter light in the same way what a normal surface without any object would have scattered. Okay. So, that way an object with a carpet on top will behave like a flat surface. Okay. So, you have to manipulate the scattered waves in that particular manner. Okay. So, here you can see when the acoustic waves propagate to the clocking carpet from a certain direction, the reflection orientation of the waves should have been scattered, okay, becomes consistent just like a mirror, as if it is coming from a flat surface. So, this is how it should look like. So, assume there is nothing here, waves falling like this would have gone in this way, right. That is how typical reflection would have worked. Now, you have got an object here, you put the carpet cloak to hide it. So, with the carpet cloak also the reflected waves should go in the same direction. So, you will not be able to see any object over here, right. So, people have also taken this further to make a 3-dimensional acoustic cloaking metamaterial, which is typically of this cone shaped, that can be fabricated using plastic through 3D printing techniques. Okay. So, this is the cross sectional illustration of the basic groove structure. So, this is how the groove looks like, okay, and this is the entire sample that has been fabricated. And what you see here is this is the simulated and experimental result. Okay. So, these are the two regions. So, here you see this is a basically flat surface, and this is the flat surface with this particular carpet cloak on it. But the reflected field region 1 they look similar, region 2 also looks similar. That means a flat ground and an object within a cloak, they basically look same. That means you are basically able to hide that particular object. Okay. So, here what is important to notice that the spherical incident and the reflected fields basically strongly interfere with each other, results in discontinuous wave fronts, as you can see in this particular figure. When the object is basically covered by the matter surface, the reflected and the total field pattern are restored respectively to that of the case of the flat ground. So, that is most important, and this results basically confirm the cloaking effect of the acoustic matter surface for a spherical incident wave. Next, we move on to another domain, which is thermal metamaterials. So, thermal metamaterials also have unique capabilities of controlling heat transfer. So, heat transfer and thermodynamics are also now of central importance to modern technologies, including power generation and conversion, night vision, microelectronics, aerospace, etc. So, thermal metamaterials could also help to dissipate heat in a deterministic or prescribed manner, and it can help you avoid local hotspots in advanced nanoscale devices. So, heating also becomes very important, and using thermal metamaterials you can control the effect of heating, right. So, you can think of some examples like thermal shields or camouflages to protect an area from transient diffusive heat flow. You can think of thermal concentrators that can focus thermal flux on a small area, thermal inverters also called as thermal rotators. They basically can help you change the direction of the thermal gradient in an area. Okay. So, couple of thermal metamaterial devices would be like cloaks. So, they can map between point and the region, eliminating the thermal gradient. So, you can hide some thermal source with using a cloak. Rotator inverter can change the direction of the temperature gradient, as we discussed. Camouflage. Okay. So, this is very important in night vision and military applications, where you can make one object appear to have another object's property. Something like a conducting cylinder, okay, may look or appear like two insulating segments. Okay. So, you can hide or disguise your weapons or something from the military perspective, right. So, you can also think of equivalent temperature profile of camouflage illusion with two insulating segments actually present and no conducting cylinder. So, that way you can hide bullets and all those things. So, these things are good for military applications. So, here are some examples and how they are made. So, a thermal shield is basically made of concentric layered structure of latex rubber and silicon elastomer. So, this is a shield. So, you can see this area is not getting the heat, it is basically shielded by this particular shield. Next is the thermal concentrator. So, here is the other way, you basically focus more heat in the center. So, it is basically made of azimuthally alternating layers of latex and elastomers. Okay. So, you have material A and material B periodically altering azimuthally. Okay. So, you can see whatever is the flux here, you can concentrate more over here, and then you also can have thermal inverter, which is made of this kind of spiral arrangement of copper and polyurethane. Okay. So, what happens here is that you can actually invert the thermal flux at the center. So, three different metamaterials basically have three completely different applications. So, that tells you the range of applications you can make metamaterials work for you. And the last topic that we will be covering today is mechanical metamaterials. Obviously, the mechanical properties in this case of a material are not basically determined by its chemical composition, but also significantly influenced by architecture of the constituents. Okay. So, although the strength of normal materials substantially degrades with reduced constituent density, natural cellular materials something like honeycomb, then trabecular bone or sponge are found to combine low weight and high strength simultaneously. So, that is something counterintuitive. So, you are reducing the density, but yet you are getting higher strength. So, inspired by this, people have or researchers have made ultra light and ultra stiff mechanical metamaterials through a network of nearly isotropic macro scale unit cells. Those have got high structural connectivity and nanoscale features, whose structural members are basically designed to carry loads in tension or compression. So, for the stretch dominating structures, the scaling relationship between the Young's modulus and the yield strength with the material's density can be linear, in contrast to bending dominated structure, where the yield strength would vary exponentially with the density of the materials. So, this is something particularly for metamaterials in the mechanical domain, but why it is important, because in these days if you want to make a product for a particular application, you need to think of all these different aspects, not only the electromagnetics, you also need to think about how the heat will be managed, how mechanically you will be making the product rigid, and it should be able to withstand any external blow to still function, right. So, according to their unprecedented mechanical properties, these mechanical metamaterials have been further classified into several categories like auxetic metamaterials, pentamode metamaterials and chiral metamaterials. So, a lot of work happening in this area as well in the mechanical departments. Okay. So, this is also something you got to understand, that it is not metamaterial field is now getting into all different domains. So, here you see an unit cell that allows ultra light and ultra strong metamaterials. So, the SEM image of the fabricated truss lattice with thin walled hollow structures is shown here. This is a 3D re-entrant unit cell. The photographs of the auxetic metamaterials fabricated using electron beam melting is shown here. So, what is this particular truss? So, a truss is basically an assembly of members such as beams connected by nodes that creates a rigid structure. A lattice truss basically provides increased structural stability due to its dispersion of forces, because it is typically designed with more unit numbers than are required. Now, when you come to auxetic metamaterials, they refer to a class of materials with 0 or negative Poisson's ratio, that is defined as the ratio of minus epsilon t by epsilon L, where epsilon t is basically the transverse and epsilon L is the axial or the longitudinal strain, right. So, this is an example of pentamode metamaterial characterized by vanishing shear modulus. So, a SEM image shows a rigid hollow cylinder and cloaking shell as an electro mechanical cloak, allowing objects inside this hollow to be unfillable. So, you cannot actually go and touch that particular object what you are keeping here. So, no mechanical pressure can actually reach there. Similarly, unit cells over here shows chiral metamaterials. So, they enables the twist degree of freedom. So, the SEM image on the left shows the fabricated one, okay, the twist under compression, and the simulated displacement field is shown on the right. Okay. So, these chiral metamaterials are basically twist when subjected to compressive forces. Okay. So, usually the lateral twist angle can reach 2 degrees per axial strain beyond the Cauchy elasticity, the typical ones. Okay. So, some chiral metamaterials can also exhibit negative Poisson's ratio. Okay. So, in addition, you can also think of origami and kirigami inspired mechanical metamaterials, which are also attracting attentions, and the deformation mechanism includes negative Poisson's ratio, multi-stability, ultra large deformation, programmable stiffness, and so on. So, you can think of a mechanical engineering domain with these metamaterials which are showing properties which are never found in the natural materials. So, something very similar to what we discussed about the electromagnetic metamaterials. So, with that we will conclude our lecture. If you have got any queries regarding this lecture, please mention the course name and the lecture number and email to this particular email address. Thank you.